Okay, in project 5, see what we got. We got a couple of cars. Let's say car 1 and car 2, and one in front of the other. Looks like car 1 is initially at rest and car 2 behind, just as I've got it. So this one's got a spring on it, and I'll draw the situation at time 0. I'm going to call this the positive x direction, and I'm going to characterize where 2 is by that point on 2, and characterize 1 is by that point on 1. So at time 0, when the spring just begins to make contact, the x1 is, I'll call that x1 0. It's equal to L0. And x2 0 is equal to 0. And then a little later on, this guy, by the way, has some velocity at this time, so we'll give it v20, whatever that turns out to be, and the spring is characterized by a spring constant k. But this is at time 0, at t equals 0. So later, car 2 will come forward, compressing the spring. Car 1 will start moving off. We'll have car 2 at some position like this. The spring will probably be shorter. The spring will be shorter. It'll be compressed during the collision. And now they're both moving. So that'll be V2 and V1. And the spring length, L, is going to be, L is equal to x1, so the position of this mark on x, the position of that mark, so it'll be x1 minus x2. That'll always be true. So the stretch is the length minus L0, which is x1 minus x2 minus L0. So we can call that x is equal to x1 minus L0 minus x2. And that's important because it'll help determine how much force is being exerted on these guys. Let's draw a free body diagram for car number 1. So it's got the spring force Fs acting on it, and then a normal force and a gravitational force, and it'll be experiencing an acceleration in this direction. We can say the sum of the forces to the right is equal to the mass times the acceleration to the right, and better call this A1 because 2 and 1 will be experiencing different accelerations. So I'll call this Fs is equal to m(a1). The masses of the two cars are the same, so it is okay to use the same symbol, m. So a1 is Fs over m, which means a1 is kx over m, where k is the spring constant, And I've got an expression for x, so let's say 1. Now from symmetry, the spring exerts both the same force at both ends, but in opposite directions. It's almost part of the same interaction. Actually, if you consider the whole spring the same interaction, we can call it that. But really, I would say the spring's exerting a force on 1, 1's exerting a force back on the spring. But over here, 2's exerting force on the spring's exerting force back on 2. But the force exerted by the spring, where it is in contact with something, just depends on how much it's stretched or compressed. It doesn't matter whether you're looking at the contact point over here or over here. As far as the magnitude is concerned, only the direction. So 2 is experiencing a leftward force, and it's got the same mass, and that's the only force. So I would say by that symmetry argument, I'll call it just by symmetry. You could draw another free body diagram and analyze that one as well, but by symmetry, I think that's 2m symmetry. We have a2 is equal to minus a1. Alright. I think I got everything I need to get started on a table that I'm going to use to analyze this problem. I'm going to define an integer. I'll call it n. So when I'm working on the nth step, n just goes 1, 2, etc. 3, ... I'll call it. And then I wanted to say what time it is. So I'm going to say delta t. I'm going to create a small time interval. I'll probably have to play with that. I'll consider that something to be determined experimentally. But I'm going to start with delta t is equal to 1 second. So the time, the nth time. So what I'm going to do is step through this in integer steps here, and I want to step through it in tiny time intervals. So the time would just be n minus 1 times t. So when I'm working on the first step, that's times 0. Second step will be, oops, not times t, but times delta t. And I'll call that t sub n. So the nth time that I'm dealing with is n minus 1 times delta t. Time 1 is 0. Time 2 will be 0.01 seconds. Time 3, 0.02 seconds, unless I change that. And I want to be able to change that quite easily, so that's why I'm keeping it as a separate number. And then I want to calculate, I think I'm going to go essentially the position of 1, but I'm going to call it x1 minus L0, the nth value of that. And that starts out at 0 because x1 starts out at x1 0 is L0. So in other words, the starting position for this, for our starting the stopwatch, is when the spring first touches car 1, and that's when at that instant the position of car 2 is what I defined as position 0, and car 1 is L0 ahead of that, so exactly the length of the unstretched spring. So x1 minus L0 is just 0 at that time. Alright. So far I haven't really outlined my plan. My big idea is just to use the definition of velocity, which is delta x by delta t, solved for delta x, to find out how far the thing's going to move in a short time step, treating the velocity constant by that and during that time step, which I'll consider okay because I'll make it such a tiny time step. And then the other piece to the argument is going to be that a is delta v by delta t, meaning delta v is just a delta t, so I'm using the definition of acceleration. And again, I'm going to find the change in velocity, and going from one time step to the next as acceleration times delta t, treating the acceleration as constant, and I'll justify that by saying, well, I'm choosing such a tiny time step that it doesn't have time to change over that, and if it doesn't work out the way I want it to, I'll change it to a smaller time step. I think my table is running into these values, so I'm going to, by symmetry, A2 is minus A1. That's also going to be a useful formula. Alright, so x2 would be the next thing I need. x2. I think I might I want to work up to the next one in case I've drawn that line too close. So this will just be copied down. x1 minus L0. The next one will be x1 minus L0 n minus 1, which is 0 to start with. So in other words, the n minus 1 means the one before it. And then times, or plus, and I think I do need some more room here, so that's why I wanted to do this second row. So plus, and then my idea up here is change in position is v delta t. So I'll go v, use the old v sub n minus 1, and that's actually v1. I'm working on v1, and then sub step n minus 1, oops, n minus 1, so the value before it, times delta t. Alright, so I need a little bit more room than I allowed for there. Let's make some more room and extend this line across. Alright, now I think I'm ready for x2. I'll do the first two values for it. See, after that it'll just always be the same thing. Ditto marks for number 3 and on down. It's just the same exact thing. Like this one will be whatever this value turns out to be, plus what the v1 for this row is, which is 2 at this stage, times the delta t. Alright, then what do you have? x2, nth value. x2 started out at 0. At time 0, so when the spring first touched 1, that's when I'm starting the clock. So, and the dot is at 0 at that time. The dot on car 2, so it starts out at 0. And then the next delta t later, it'll be at x2 of n minus 1. So n minus 1 is the one before, in other words, the 0 this first time, plus whatever v2 is, and I'll go from this row as well, from the previous row. So I'll call v2 not of the current time, but of n minus 1. So of, well, I'm working on this one, it'll be row 1, but when I'm on the next one, it'll be the row 2, and then times delta t. And I don't like the way that delta t came out, so delta t. Alright. And then the next one, the third one would be the same thing, etc. Working our way down. Okay. Then what? Let's get the spring compression. I'm considering x to be the amount the spring is stretched or compressed, but it's the, in this case, just the compression. I'll use a positive value for the compression. So, let's see if I got this right. The amount the spring is compressed is actually the opposite order for these two, so I want to fix that up. So it'd be L0 minus L for the amount by which it's compressed. So that'll be a positive value in that it's always compressed. And so that's, let's see if I can fix that up. It's L0 minus that. Not a very convincing L0. L0 minus that. So x is equal to L0 minus all that. And that would be x2 and then minus this stuff. So it's just the same expression in the opposite order. x2 minus, I think I'll just copy that all over. So as I distribute that minus sign, I get a positive x2 and then minus x1 minus L0. When I use this x1 minus L0, it's just how far out in front x1 is of its original value. So however far over it is, like over here, I subtract off the L0, and that's how far it is ahead of there. So I've intentionally chosen to use that. So that looks good for x. So I'll go, originally the amount of stretch is 0. In general, the amount of stretch is just, I guess I could actually leave it like that. It's, I can put it right up here. So for the first one, it's x2 minus x1 minus L0. Now, I never really know what L0 is. I'm using a value for x1 minus x0 in this expression. And by the way, this is the nth one, the row that I'm actually on. It's the nth x2 as well. And then this is just ditto marks straight down the line. So for the rest of the table, this imaginary table I'm creating, I'm not actually going to fill in 1,000 values or anything, but we got the stretch of the spring. Okay, based on the stretch of the spring, I should be able to get the acceleration. So both A1 and A2 will calculate A1 and A2. So I got the expressions right there for them. So I'll go A1 is just k times x, the nth value of whatever x is. So the row that I'm working on, all divided by m. And then A2, I think I can get that a smaller column. A2, the nth value, has to be the nth value as well. And then that gets copied down, so the second row would have the same thing, third row the same thing, except this time, the second time, xn is the one that's right to the left of it. And for every other row, it's the one right to the left of it. It's not always this first one. And this is just minus A1 nth value. And same for subsequent entries. And now I need the velocity of this thing. So I go the velocity of number 1, that's the one that's out front. V1, the nth value, is going to be equal to I think the first one, I'll say it's just 0. And the second one is going to be V1n. That's what I'm actually solving for. So the second one is going to be the previous one. So I should go V1 n minus 1. Oops, minus 1. plus the acceleration times the time. In other words, I'm just using the definition of acceleration. Delta t. I want that to look like a delta t, but I think I'm using a1 nth value and then times delta t. Alright, again, that's just from the definition of acceleration. That's the little formula that I had up here. Delta v is a times delta t. So the new velocity is the old velocity plus the delta v, which is a delta t. And the new velocity is the old velocity, which would be the one before it, plus a times delta t. And same thing for v2. At least the same idea, not the exact same expression. v2, so the velocity of cart number 2, nth value. The first one will be v20. That's given to me by the user of the program. That and k were the two arguments. So v2 at any other time is going to be the old one, the previous one, v2 n minus 1 plus a2, the nth value, should be over here someplace, yeah, well, right in here for the second item, nth value times delta t. Okay, so I think as far as algebraic solution, I got everything there. Now I got to outline the code. So I go step 1, take what is it, k and v20 as arguments. Takes as argument the value of speed of car 2, that's v20 and k, v20 and k. v20 and k as args. Set m equal to whatever they said it was, 1,000 kilograms. Set m equal to 1,000 kilograms. And I'm going to go set, I think I'll call it a step 2, set delta t equal 0.01 seconds, but might, I don't know, I think I should say, but experiment with this. Experiment with this value. Alright, now 3, I think I got some more stuff to set. Let's see how I get started here. Set t of n. Let n is equal to 1. Let's try that. Set n equal to 1. And then I want to start calculating these things on the table. So I'm going to have to do a loop. I want to see how to get it started is the thing. So I think I'll leave a little bit of room there in case I got some more stuff to set equal to something. I'm going to go for while, what is our condition? I think xn is greater than or equal to 0. So xn is how much the spring is compressed, and as long as the spring is compressed a little bit, then we want to keep on going. So the instant it becomes uncompressed, then we stop. So while x sub n is greater than or equal to 0, we want to do the following stuff. Let's see what we got to do. Calculate t sub n. And I think I might want to, I don't think I want to put ABC. I'll go n is equal to n plus 1. And I think all this other stuff, I'm going to go ahead and calculate the first row for a while. So T, I need to make a graph of force versus the I think I need another column in here because I need the force. I'm supposed to be graphing force versus time, so let's calculate the force as well. So the force is kx, so I think I know what I gotta do. Kx over m, I better not forget that. So I'll call this f sub n, and then this a1 sub n. So I got two, I just split that into two columns. The force is kx sub n, and the x sub n is the value that's just to the left there. And then the acceleration is the force divided by the mass. Alright, because I need the force, I think it's a good idea to have the force in the column since I'm trying to graph force versus time. So I need to save time values, and I need to save force values. So I'll say I'm going to go t of 1 equals 0. That's the first time value. So I'm starting to build up an array of time values. And there's the first element. And then I'll set x1 minus L0 equal to 0. Set, I'll call that x1 ml0. I think I'll leave it x1 minus L0. Set that equal to 0. You don't need to save those values, so that's the first one, but hopefully I don't need to save it. And then x2 doesn't need to be saved, so set x2 equal to 0. And what else have I got here? So set xn equal to, and this is actually 0, so rather than calculate it before I get into the loop, I will put this down here. So x2 n minus x1 minus L0, and that's how much is stretched, but how much is stretched at time 0 is 0. That would evaluate to 0 anyway, but I'd rather just type in the 0 for the getting started phase. So I'll call that 0. And then the force is 0 as well. I think I'll put the k xn down there, because k times 0 is 0. So I'll just start that out at 0. So Fn, I'm going to call that f of 1 equals 0. So I've got to save the f value. So I'm starting to build up an array there. The first element is 0. And then what else do I need? A1 is 0. So I'm not even going to be typing in any of those names yet. So Fn over m, or any of these expressions, I mean. So I'm just going to type in a 0 for that one. The force starts out at 0 at time 0, and then minus a1 nth value. But that starts out at 0 as well. The acceleration is 0 at the start. Zero. So I think F1, so A1 equals 0, A2 equals 0, and then V1 equals 0, and V2 equals 0. Those will correspond to the nth values. That's actually the very first value, but I'm not putting subscripts in there for real, except for on the force and the time, because I need to graph those. So those are the ones that I really need. So, well, so I got the n is equal to 1 values. So while xn is greater than or equal to 0, and it starts out at 0, so I should get into this this region of the loop. I'm going to bump up n by 1. I'm going to say t of n. So at this point, it would be 2. I'm thinking about the value of it rather than writing the symbol. But t of n is equal to n times delta t, and I think I just have to essentially copy down the formulas from my table. X1 minus L0. So I'm going to have to make up a variable name for that, I think. I'm going to use the word minus in there when I actually program it up, but X1 minus L0 is the old value, and then plus the old value of V1 times delta t. So so this represents the old value, and then plus V1 times delta t. And what's stored in V1 right now is the old value. What's stored in this variable, I should probably underline it to let you know it's a whole variable rather than an actual mathematical expression. So this is the equal sign here in most programming languages is actually referred to as an assignment statement. So what we do is calculate what's on the right and assign that to what's on the left. So what's on the right is the contents of this variable plus the product here, and then I assign it to the same variable that I use, but first I calculate it and then I assign it, so there's no conflict there, as there would be. Like, that's obviously not an equation. That can't be true unless V1 times delta t is 0. So this is an assignment statement in MATLAB, not an equation. Alright, so what do we have next? probably x2. So same idea. So the new value of x2 is equal to the old value plus v2 times delta t. This is the definition of velocity, really, but we're treating it as being constant because delta t is such a short time interval. We should be able to get away with it. And if not, I make it shorter. So then I got to get xn, which is the difference between those two. So it's the second one minus the first one. So xn, I'll just call it x, is x2 minus the x1 minus L0 variable, I think. Yeah. And then fn, in this I want to go f of n. So n is going to be 2 the first time I get through here. So that'll be the second element in my array of forces, is just k times x. I want to make sure I've established what k is. Yeah, I took k as an argument, so that's cool. So after x, we got the force, and then comes then come the two accelerations. So we're using A1, the one that's up front, is f of n divided by m. And A2, the one in the back, getting pushed backwards, is minus A1. So what else we got? The two accelerations, now the velocities. So I'm essentially just using the velocities. Definition, v is a times t, or delta v is a times t. So v1 is equal to the old value of v1 plus a1. Which order did I do them in up here? Might as well keep it the same. Yeah, okay. I am keeping it the same. So a1 times delta t. Not being consistent with the asterisk. Sometimes I put it in, sometimes I don't. I think it's alright. v2 plus a2 times delta t. I think I've gotten to the end of the table. So that's going to be the end of my while loop. So I'll type in an end over here, hopefully right under the word while. Let's see where I'm at on that. No, kind of. And then when I get done, what happens? You get to the end here, and then it goes back up and checks again, is xn greater than or equal to 0. And it's really, I'm calling it x rather than xn, so I think I'll erase the n in both places. So erase it there, and then the idea is it goes through the loop once, then it goes back up and it checks to see if x is greater than or equal to 0. If it is, it does the loop again. So the first time it bumped up n to 2, now it'll bump it up to 3. This is the same idea. It's an assignment statement, not an equal. That's not an equation. So it calculates n plus 1 and then it evaluates that result and assigns it to n. So what was in n gets replaced with the new value. So a minute ago n was 2, or the last time through this loop n was 2. Well, when we came into the loop the first time it was 1, now it's 2, so 2 plus 1 makes that 3, and n just keeps on increasing, and then we keep on increasing the time, calculating everything, and eventually anticipating that the two cards will come apart, and at that instant, the first instant that they come apart, the first time, the compression is less than 0. We don't do the loop anymore, so we're all done. We've gotten down to the point where they're coming loose from the spring, or card 2, the one that's ahead, card 1 is coming loose from the spring. Okay, so at that point, we should have filled up the F array with values of force and the time array with values of time. So we can say in step 5, up to 5, plot T, comma F. The 2 arrays that we created and all that. Let's see if it really was up to step 5. So, yeah, 1, 2, 3, 4. 4 was the big while loop. And then 5. Okay, so I think I've done the algebraic solution and the outline of the code. And so I'm going to call it a wrap, but beware, as I program it, I might find mistakes in this part of it, so I'll have to come back and fix it. So make sure you're aware of the whole project rather than just thinking that this is it. I'm pretty confident that what I got there is right, but sometimes you try it. If it doesn't work, then we got to fix something up, and we might have to come all the way back here to the pencil and paper part of the solution to fix it up. So this is a wrap for project number 5, video number 1.